Let's take a look at one last example of the root test and see what it tells us. Now I should point out that the root test also has inconclusive cases, just like the ratio test does. We haven't looked at an example of that, but there are plenty of those in the Pearson problems and also in the problems in the textbook. So if you want to play around with that, go take a look at the Pearson MyLab. You'll see plenty of examples of that. So here for example 3, we're going to take the sum n equals 1 to infinity of n to the n divided by 3 to the power 2n. So this one, again, we're going to hit it with the root test. And here we're going to have this r, which is going to be the limit as n goes to infinity of the nth root of all of that stuff. So here we're going to get n to the n over 3 to the 2n. And we're going to go ahead and we're going to take the nth root of that. And here the only tricky part is remembering our exponent rules. So this is going to be the limit as n goes to infinity of, in our numerator we're going to get n. And in our denominator we're going to get 3 squared. Oh, and look, this is infinite. So the series diverges. There are a few limits that knowing them and recognizing them will make your life a lot easier. And both of them can be done by L'Hopital's rule, but you have to know where to look in order to use L'Hopital's rule on them. So let's take a quick look at those. I think those are going to be two very useful tricks to keep in your tool belt so that you know how to use them. So the first limit that's really useful to know is that the limit of the nth root of n, if you take the limit as n goes to infinity, you get 1. So let's figure that out or demonstrate it, though knowing this is all you really need. Right? So this is going to be the limit as n goes to infinity of n to the 1 over nth power. And here we're going to use a very useful fact. I'm going to put this over here on the side. This is that if I raise a to the power b, that's the same thing as e to the b natural log of a. And that's a super duper useful identity. I recommend really being comfortable with it. Okay, so coming back over here, that tells us that this is the limit as n goes to infinity. Here we get e to the 1 over n natural log of n. And as we saw before, right, the fundamental log limit tells us that this guy is going to 0 by the fundamental log limit. You can also get that by using L'Hopital's rule if you prefer, right? This is natural log of n over n. That's infinity over infinity. You can use L'Hopital's rule on it. I'm not going to do that. Instead, I'm just going to use this fact. That's going to give us e to the limit as n goes to infinity of 1 over n natural log of n. And we just said that that's going to 0. So that's e to the 0. So that's 1. Okay, so that's a first useful limit that's good to know and to be comfortable with, or at least, right, if you may not remember it, at least remember the steps of how we got there. Right, so that derivation is a useful one to know about. And we're going to see one more similar one, where we look at the limit as n goes to infinity of the quantity 1 plus a divided by n, but raised to the nth power. And whatever it is, we're going to end up with e to the a, where this a, right, so a is a constant that doesn't depend on n, right? So that's an essential assumption in this formula. So let's figure this one out. This is going to be a L'Hopital's rule game again. Right, so here we get the limit as n goes to infinity of 1 plus a over n to the nth power. Well, we use our exponential identity. This is going to be the limit as n goes to infinity of now e to the n natural log 1 plus a over n. And now we need to figure out what the limit of this is, right? So this is going to be an intermediate step where what we calculate is the limit as n goes to infinity of n natural log 1 plus a over n. So this is going to be the limit, right? This looks like an infinity times 0 case. So we need to monkey with it until it looks like something where we can use L'Hopital's rule. So I'm going to put it as natural log 1 plus a over n, and then downstairs we're going to divide it by 1 over n. So this now looks like 0 over 0 as n goes to infinity, so we can hit it with L'Hopital's rule. So this is the limit as n goes to infinity of, now we get the derivative of this numerator. So that's going to give us 1 over 1 plus a over n times negative a over n squared, right? That's using the chain rule. And I took the derivative of the natural log, and that gave me this thing here. And then we took the derivative of that box to get this expression right here, right? That's applying the chain rule. And then our denominator, right, we're using L'Hopital's rule, so we take the derivative of that denominator, we get minus 1 over n squared. Our minus signs are going to cancel. And the n squared is going to cancel. We're going to get a over 1 plus a over n. And as n goes to infinity, this term here goes to 0, and we get a. Now this was an intermediate step, right? This was this thing that I've put in a box was what we got from that exponent up there. So what we're going to do now is we're going to sub that back in. Okay, so remembering that this green box here is what we found the limit of on the previous page, using L'Hopital's rule, this is going to give us e to the limit as n goes to infinity of that expression. And what we found on that previous page from that intermediate step is that that limit of that exponent is just a itself. And so that's where that limit comes from. Now, remembering that limit is maybe not of fundamental importance, but what is remembering that that limit can show up and the way that we did to figure it out. So the method is more important than the conclusion, but also being able to recognize it if it gets thrown at you is also a useful skill to have.